Hi, and welcome to our second lesson about the quote-unquote best fit line. Yesterday we looked at finding an equation for such a line by our manually. Today we're going to look at how the calculator actually calculates the least squares regression line. Two characteristics of that least squares regression line. That line must contain the centroid of the data set. Must contain the centroid. And we'll talk a little bit about what the centroid is. And secondly, it must minimize the squared error. And I'm going to put that in quotes, squared error. All right. So those are our two guides, and we're going to start out by looking at the centroid. And we're going to look at a very small data set, and I would ask you to think about what this data set looks like real quickly. X is going 1, 2, 3. Y is going from 0 to 5. 2, 3, 4, 5. So the first point is 1, 0. Right here, the second point at 2, data set says 4, so up in here, and then 3, 5 up here. Okay, real small data set. The centroid of a data set, folks, is its average x, comma, average y. Okay, it can be thought of as the balance point or the center point, an average point of the data set. So to find our centroid, we've got to have the average of the x's. So that would mean sum the x's, 1 plus 2 plus 3, which is 6, and divide by 3, since there are 3 data points. 6 divided by 3 is 2. And the average y here is 0 plus 4 plus 5, 9, divided by 3, and that's 3. So our centroid is the point 2, 3. All right, what I've done here is come up with 4 possible linear equations that could be the best fit line for our data, and you can see they're all somewhat reasonable. This one is very close to 2 of the points and is away from 1. This one, the distance of those 2 is farther from the line, but this one is closer. Here, I really like that it contains or hits 2 of the points and is very close to 1. This one hits 1 point and is real close to 2. So I'm going to just, as my best guess, say I like this one the best. But let's see what the calculator says. One of these, and I've got equations for each of them, one of these linear equations does not have the centroid. And remember, the centroid is the point where x is 2. We want to know if when we put 2 in here, we'll get 3, because the centroid was 2, 3, remember. So if x is 2 and we add 1.5, we do not get 3. We instead get 3.5. So this one is just out. This one, when we put 2 in, we do get 3. So this is a possibility. This one, when we put an x of 2 in, 2.5 times 2 is 5, and 5 minus 2 is 3. So this one is still good. This one, if we put 2 in, 2 times 2 is 4, and 4 minus 1 is indeed the 3 that we need. So all 3 of these linear equations contain the point 2, 3. They're all still good candidates. This is the only one that doesn't, so we can eliminate y equals x plus 1.5. That one is not a candidate for best fit. A second criteria for the least squared line is that the sum of squared error be as small as possible. So we're going to do a little bit of arithmetic. Sum of squared error has to be as small as possible. For each of our linear equations that remain, we're going to look for the sum of squared error. So we have an actual y here. We are going to predict a y based on this equation for each of the x values here. Then we're going to look at the amount of error, and that's going to be actual minus predicted, because that's the way we do that thing. Then we're going to square it and sum it. So when x is 1, then y would equal 1 plus 1, or 2. 0 minus 2 is negative 2, and negative 2 squared is 4. When x is 2, y will equal 2 plus 1, or 3. The error there, 4 minus 3 is 1, and 1 squared is 1. When x is 3, y is 3 plus 1, or 4, and the actual y was 5, so the prediction error is 1 again. 5 minus 4 is 1, and 1 squared is 1. That's a sum of squared error of 6. Remember, the least squares line makes that sum of squared error as small as possible. Our second candidate here, we'll find our y's by multiplying 2.5 times the given x, 1 in this case, then subtracting 2. 2.5 minus 2 is 0.5. The error is y minus predicted y, actual minus predicted, and 0 minus 0.5 is negative 0.5. When you square negative 0.5, you get 0.25. Y is equal to, now 2.5 times 2, which is 5, 5 minus 2, which is 3, and the error there, 4 minus 3 is 1, 1 squared is 1. When we put an x of 3 in here, that is going to give us 7.5 minus 2, which is 5.5. And the predicted error, 5 is, that's going to be negative as well, negative 0.5. Squaring that, 0.25. And when you sum the squared error here, you're getting 1.50. So that's certainly smaller than that one. Notice, by the way, it's necessary to square the error, because if you don't, then the sum of the error is always going to be 0, right? Squaring the error eliminates the negatives, and what we want to do is find the smallest sum of squared error. Here comes our last candidate. Y's here are 2 times the x value minus 1, and 2 times 1 is 2, minus 1 is 1, 0 minus 1 is negative, and negative 1 squared is 1. When we put our x of 2 in, 2 times 2 is 4, minus 1 is 3, 4 minus 3 is 1, and the square of 1 is 1. Finally, y would equal 2 times 3, which is 6, minus 1, and 6 minus 1 is 5. 5 minus 5 is nothing, and the square of nothing is nothing. Sum of squared error here is 2. So this was small, but it was not as small as the squared error that we got here. That would mean that this equation fits both criteria. It contains the centroid 2, 3, and it minimizes squared error. We should, and we did, get down to 1 based on our manual math that we've done here. We know that the equation for the regression line should be y equals 2.5x minus 2. We're going to verify that with the calculator. You see I have my data in list 1 and 2. Let's put the data in list 1 and 2. And then, some of you will have done this before, but we're going to use the stat and calc options. So I'm going to go ahead and get into stat. She says stat and over to calc. And we've used the one variable stats before, but if you look down below, there are all different kinds of regression models that are available here. We want the linear regression since our data looked linear. Your calculator may have different requirements here, but basically our x's are in list 1, our y's are in list 2. The frequency list, if you have something there, you just need to clear it out. We don't want anything there. We don't want to store, although we'll show you in a moment how to do that. What we want to do is calculate the regression equation. So it was stat, calc, and then option 4, lin or linear regression, lin reg. And you can see the calculator agrees with us. It says that following a y equals ax plus b model, where a is 2.5 and b is -2, is the best fit line. You can see, folks, that we have a relatively strong correlation here. Some of you will remember that from last year, and we'll talk more about that. To get this equation into the y equals of our calculator, first things first, we're going to clear out anything that is in the y equals. With that on our screen, we hit the y equals key. The paste function is under vars, and I'll write this down in a minute. 5, I always think a scatter plot is a statistical plot, so we want the statistics, and then we want an equation, so I'm going to arrow to the right until I get to EQ, and then reg EQ is the first option. And there it puts it in there for me, so I don't have to retype it, which is kind of nice. So to get that paste function again, it was clear y equals if necessary. And then it is vars 5 for statistics over twice to EQ and choose reg EQ should be the first option. Unless you're on a TI-82, then you have to arrow down to find reg EQ. But vars 5 over reg EQ will get us that. And let's just see how that looks with our scatter plot. I've already set up a good viewing window for this. So there's our data and there's our line. And yes sirree, that looks like a pretty darn good fit. Okay, let's try that again, only now with a slightly more complicated problem. The question is the magnitude of an earthquake related to the depth below the surface at which the quake occurs? X is the magnitude of an earthquake on the Richter scale. Y is the depth in kilometers of the quake below the surface. It says use your calculator to create a scatter plot, then find the equation of that least squares regression line and add it to the plot. Then, once we have that done, we're going to use our equation to predict the depth below the surface if a quake measures 3.7 on the Richter scale. Alright, let's get the data in the list to start with. I'm going to go ahead and type mine in, and I will catch back up with you in just a minute. Okay, I have my data in the list. I'm going to go ahead and create my scatter plot. So I want to clear out what's in my y equals because I don't want that to mess with my equation. Set up a viewing window. Well, these y's are basically bigger than 2 and less than 5. I'm going to just tell mine to start at 0. I like to have things start at the beginning, and I'm going to put a max of 5 in my x's. Scale of 1 is good. The y's are telling us the depth below the surface, and you can see the smallest is 3.9 kilometers while the largest is 11.2. I'm going to go from 0 to 12, since that'll cover my range by ones. And let's just look at that scatter plot. There it is. It does look kind of scattered around a little bit, but it said to do that. And then we're to find the equation of the least squares regression line and add that to the plot. So stat, over to calc, choose lin reg, arrow through if your data is in 1 and 2, or change if you need to. And here's the equation of the line, which I'm going to write right here. I'm going to round my coefficients to the nearest thousandth. So 2.156x plus 0.221 basically. To paste that into my y equals, it's vars 5 over and enter on reg EQ. Now it's got that in here without my having to type or round. If you'll notice that I've got lots and lots of digits of precision. I believe it gives you 10 digits. So let's take a look at the graph with the line in it, and there you have it. What this is saying is that we want to use our equation next to predict the depth below the surface if a quake measures 3.7 on the Richter scale. Now, ladies and gentlemen, I see that our line hits one point, and it does divide them equally above and below, but I'm not sure how good our prediction will be. We can definitely make one, but I don't know how good it will be. The x that we are interested in is that 3.7 on the Richter scale. And let's go over here and see 2.156 times 3.7 plus 0.221. They say around 8.2 to the nearest tenth, and that would be kilometers below the surface. I would like to draw your attention back to our graph screen, folks, because your calculator can also do this computation for you. Second and trace opens up a whole list of things that you can do with a graph, and what we want to do is enter an x value, which is option 1, value. The x we're interested in is 3.7, and it says, this is the calculator now, we did second, trace, and value to enter an x value. It says that when x is 3.7, y is about, well geez, look at that, 8.2. Okay, both ways work fine. The one thing I would say about this is we rounded here. Our calculator goes to way more digits of precision than we do. It goes out to like 10 places past the decimal, so their estimate is probably a little bit better than ours, but as long as we carry our equation out to 3 or 4 places past the decimal, most of the time that will be sufficient. So, okay, that's the end of our lesson for today. I'm going to say please get out there and do that. You try as quickly as you can. I'll see you in class.